Hello, my dear NEET warriors. Welcome to the Unacademy NEET English channel. And this is your physics educator, Captain Shreyas. I hope I'm audible as well as visible to all of you. Nice to see all of you on this lovely evening. And today we are going to do in this detailed marathon session the complete chapter of electromagnetic induction. If you are not aware, let me remind you, compulsory one question from this chapter. There is a good chance that you might get up to 3 questions that carries totally 12 marks from this chapter alone. So gear up, buckle up, because for sure you are going to score those 12 marks if it comes in the examination by just this particular lecture. With me, Shreyas, your physics educator. And to proceed ahead, you need to do a small favor. You need to go ahead, smash the like button, mark your attendance, show that interest so that even YouTube understands, listen, this student is interested in studies. Let's not show him distracting content. Number 2, you have to be subscribed or else you will miss my classes. Nice to see all of you out here after a long time. Hello Ritugna, hello Sonia, hello Priyanka, hello Subhashni, hello Anil. Missed you all a lot for a long time. We had a blackout week and so many other things, activities. So here we are geared up, and I'll be starting after a week. We will be starting with 11th standard portions also. I mean, we have already done till almost circular motion or work power energy, close to that. So we'll continue from that part wherever we had stopped. So gear up for 11th standard remaining portions as well. Okay, so show your support, show your love by smashing the like button. Thank you so much, guys. So let's begin with the class. And today we are going to see Faraday's law, then we are going to see Lenz's law, then we are going to see motional EMF and eddy currents, and then we'll go to inductors and inductance. So that is the main thing in this chapter. 4 things are there, basic concepts are there, and then you have to use it in different ways, combining it with different aspects. That's all that you have to learn in this chapter. All right. So let's start with Faraday's law in detail. Now, do you remember the quantity called magnetic flux? Because that is needed for studying Faraday's law. If you have forgotten, let me remind you, no issues. See, if you take some area, let's say that area has some vector shown like this, and maybe there is a magnetic field cutting through it. Let's say this is the magnetic field which is cutting through that particular area. So the field lines are basically piercing that particular area. So there is something called as the magnetic flux associated with it. So there is magnetic flux, and that magnetic flux phi, you can say that is equal to the magnetic field dot product with the area vector, or you can just put it as BA cos of theta, where theta is the angle between the area vector and the magnetic field. Both are the same thing. It's a scalar quantity. Remember that it is a scalar quantity, and the unit of this particular magnetic flux is Weber, and 1 Weber, like you can see, is 1 Tesla into 1 meter square. 1 Tesla. So 1 Weber is 1 Tesla into 1 meter square. That's what it is. You remember this? Most of you remember this from the previous magnetism chapter. Very good, Deepthi. Good evening, Elva. Very good evening, Mohammed. Yes, awesome, Deepthi, awesome. Hi, Kailash. Hello, good evening, real life. Now, this flux talks about how much field is going through an area. More field goes, more flux. Now, how can you change the flux? Can you guys guess? What are the different ways of changing the flux? Imagine there is a particular area. Okay, imagine there is a particular area, and this is that particular area vector, and there is some magnetic field cutting through it. How can you change the flux? What are the different ways of essentially changing the flux? Because that will be important for Faraday's law. What are the different ways of changing the flux? Number one method is changing the field itself. Imagine first the field is weak, then you make it strong, more field lines go through it. Or it was strong, you make it weak. So when you change the field, obviously the flux will change. That's number one way. Very good. What can be the number two way? Think about it. The number two way is obviously changing the area. If that area is changed, I will see more field lines passing through it. If I make the area small, few field lines will pass through it. So obviously I can say changing the area itself. Changing the area itself. If I have a small area, I make that area big, or big area, I make it small. More or less field lines will cut through it. Obviously flux will change. I think there is one more way. Let's see who are the smart ones in the chat box who can tell me what is the third way of changing the flux. Come on, my dear students. Yes, Sangeeta, obviously there will be PYQ sessions, mock test sessions, revision sessions, everything for all of you. But let's first complete the syllabus. That is on number one priority. Every other session will follow. I want you to first focus on the syllabus completion. Wow, we have very smart people in the chat box, yeah? I can see NEET toppers in the chat box. Look at that. Ritigna, Subhashini, Vadanjani, Priyanka. Awesome, yaar. Awesome. Obviously, by changing the angle, change the orientation. Change the orientation. So, basically, imagine the loop was pointing here, then you make it point here. So, the area vector will change the direction. Obviously, theta will change. Obviously, theta will change, and you can see that the value of the flux will change. So, either you change B, or you change the area, or you change the orientation, that is basically the angle. Perfect. Now, why do I need this? Why did I make you study the change in flux? Because I'm going to teach you Faraday's law. See, everybody remembers, what did Oersted discover? What did Oersted discover? He said that there is a wire which carries some current. What does that current create? What does that current create? The current creates a magnetic field. The current creates a magnetic field around it. What Faraday thought was, the exact opposite. He thought, if I have a magnet, can I create current around it? Can I create voltage around it? That is what he thought. So he performed many experiments, and he finally discovered what creates electricity. Did you understand? It is exactly opposite of Oersted. Oersted discovered that current carrying wires produce magnetic field around it. What Faraday discovered was, when you take magnets and you do certain things with it, then you can create electricity with it. Exactly opposite. Good evening, RB. Thank you for the lovely hearts. So, what did finally Faraday discover? So, Faraday's law says like this. Faraday's law. According to him, changing magnetic flux, not constant, changing. It should increase or it should decrease. Changing magnetic flux induces electricity. Induces electricity in a loop. So that creates something called as the induced EMF. And because there is EMF in that particular coil or that loop, the coil might have some resistance. That resistance decides the induced current. The resistance decides the induced current, because induced current will be the induced EMF divided by the resistance. So whenever flux changes in a coil, it is found that electricity is created, and in that loop, the electricity EMF generated, it behaves like a battery. That EMF generated is going to decide how much current will be created along with the resistance. And he saw that this particular induced EMF is equal to the rate of change of flux, is equal to the rate of change of the flux, rate of the change of the flux, how quickly the flux changes. So it is nothing but d phi by dt, magnitude wise only we are talking about. Later on we will check the sign using Lenz's law. For now just remember the magnitude is d phi by dt, derivative of the flux with respect to time. That means just like rate of change of velocity gives you acceleration, rate of change of position gives you velocity, like that only rate of change of flux gives you EMF. Is that part understood, my dear students? So this is the main formula of your Faraday's law. This is the main formula of your Faraday's law. Also bear this in mind, if I had a graph of flux versus time, and let's say by chance the graph was like this, some random way in which the flux is changing, and by chance I happen to draw a tangent to it. If I draw a tangent to this particular curve, can you guess what will be the slope representing? Think about it. Slope is rate of change of y with respect to x-axis. Y is flux, x is time. So isn't this basically d phi by dt? So what is it actually telling me, the slope? It is telling me the induced EMF. Everybody understanding this point? Very good. You are Chetna, you can join my classes using the link in the description box. If you are a part of the Plus, Iconic, or even the normal course you can buy, right? The link is there in the description box. Just check for NEET energized batch. That's all. You will be able to join it. Hello Yashwant, good evening. Now that you understand this is Faraday's law, how about seeing Faraday's law for yourself? So guys, this is virtual Faraday's law, right? So you are seeing me also virtually, so why not see Faraday's law also virtually? Do you see there is a coil? Do you see the coil is connected to a bulb? Do you see we have a magnet also? Also this magnet will have some magnetic field lines, something like this. For now let's not see the field lines, let's just look at the magnet. Is the bulb glowing right now? No, right? If I put a voltmeter, the voltmeter is also showing 0 reading. Now let's move the magnet. Look at that, the bulb glows. Look at that, the bulb glows as I move the magnet. If I move the magnet around here, do you see the bulb is glowing? The voltmeter is also changing the needle's position. So electricity is created by magnetism. Magnetism is creating electricity. Awesome, this is exactly what Faraday discovered. Now what is happening over here can be easily seen using the field lines. Do you see when the magnet is here, some of the field lines are cutting through the coil, some of the field lines are piercing through the coil. When you move the magnet here, do you see more flux, or basically there is a change in the flux? So if the magnet is stationary, the flux won't change. If the magnet moves, then you can see the flux changes. That's the reason why you will see there is electricity created. Exactly Faraday's law. Now the best part is I can compare two coils over here. Look at this. What is the difference between both the coils? This coil has only 2 turns. This coil has more turns, 4 turns maybe. So what happens is the same field lines will cut through each coil. So the flux will cut through the total coil 2 times. In this particular coil, through each turn the field lines will go. So through the total coil it will cut 4 times. Each coil you will see or each turn will have those field lines. So the total coil will see the flux 4 times. Can you see that? So if you move the magnet here, if there is some amount of voltage which is created, I hope you can see the needle, how much it is changing. Just make a rough mark in your head. Now take the same magnet and move it with the same speed. You will see that the voltage created is slightly more. In fact, it will be double. If you make it move over here, it is slightly less. Why? Because the number of turns have changed. So this clearly tells me the number of turns in the coil affects the total EMF produced. Is that understood, my dear students? Very good. One more observation you would have seen. If I move this magnet inside, right now it went to the left side. If I move it outside, it moves towards the right side. That means the direction of the current also will change when you change the polarities or change the direction. So again, observe this. I move it left, it deflected left side. I move it right, deflected right side. If I swap the polarities, this is north, this is south. Now I make this south, this north. You will see now the deflection will be exactly opposite. So if I move it left, it is going towards the right. If I move it right, it is going towards the left. So changing the polarities, changing the orientation or changing the direction obviously changes the direction of the electricity induced. All these are interesting observations, my dear students, which Faraday saw. So going back to this slide, so there will be quite a few questions based on this particular concept, and let's, I think, start solving this. All right, let's start solving this. Cool. So I hope you guys are ready for solving the questions, right? So here comes the first question. A magnet is moved towards a coil quickly versus slowly. The induced EMF is same in both, more in one than in two, smaller in one than in two, nothing can be said. Okay, just let's go to this same simulation. Just imagine you move the magnet slowly. There is some EMF produced. Look at the deflection. I'm moving the magnet slowly. There is some deflection. Versus I move the magnet a little bit fast. What is happening? The moment you move it fast, the EMF produced will definitely increase. Yes. We'll come to that Eva. Why minus sign? See, many students and many teachers unnecessarily confuse students by putting that minus sign. I've seen so many teachers teaching students spring force is minus kx, pseudo force is minus ma. Though technically you are right, why put that minus sign when you know the direction? I know pseudo force always acts opposite to accelerations of the frame. I know spring force always acts opposite to the x. You already showed in the diagram. Do you say G value is minus 10? No, right? I know G is down. So if I take upwards positive, G will be minus. If I take downwards positive, then G will be positive. So don't worry, don't bother about the sign, guys. Right? That sign is just merely a direction. If I say the voltage is 2 volts or if I say the voltage is minus 2 volts, it is 2 volts, whether this way or that way. So really doesn't matter. So don't worry about the minus sign. Only worry about the magnitude. Cool. So guys, the correct answer for this particular question should be more in 1 than in 2, because this is quick, this is slow. So faster rate of change. Very quickly the flux will change. More flux changes in small time, more EMF is produced. Is that right? So everyone? Yes, we will be taking center of mass. Concentrate, Yashwant, on this particular chapter for now. Concentrate on this lecture. Everything will be done. Ready, guys? Everybody show high josh, high energy, and if you have forgotten to smash the like button, do that right away, right now. Going to the next question on your screen. Whenever a magnet is moved either towards or away from a conducting coil, there is some EMF which is produced. Okay, the magnitude of which is independent of. The EMF produced is independent of, not dependent, independent of strength of the field, speed with which the magnet is moved, the number of turns of the coil, or the resistance of the coil. Think about it, my dear students. Whenever a magnet is moved either towards or away, then what do you think will be the EMF independent of? Magnetic field, definitely it will depend, because flux decides the magnetic field. Speed, do you think speed will affect? Do you think speed will affect how much EMF is produced? Exactly, we just saw the first question. More fast you move, more fast the flux will change, more EMF. Turns of the coil, I just demonstrated to you right now. More turns, more flux, more rate of change, more EMF. So all these three things, it will be dependent. Resistance, no. Resistance decides the current, not the EMF. Hence, resistance of the coil should be the answer. Very good, very good. What does resistance decide? It decides the current which is induced. The current which is induced, because that is EMF induced divided by resistance. EMF induced is basically del phi by del t, rate of change of flux. That's what it is. Awesome. D for doctor. Very good, Priyanka. Very good, Vedanjini. Rania. No, it's not B. Yes, Priyanka, it's D. Yes, Suhashini. Yes, Ritigna. Very good. Very good, baby Mitra. Indu. No, it's not B. It is D, Bidisha. Very good. Let's go on to the next question. Okay. Don't worry even if you do not get the answers right. Don't worry even if you make mistakes, because I am here to help you out. I am here to teach you. I am here to make you realize what you are thinking versus what it should be. Don't be disappointed at all, because this is a learning phase. Coil having 500 loops of this much side placed normal to the field, where the field increases at 1 Tesla per second, how much EMF is produced? Okay, let's think about what is exactly happening. There is a coil which is in the shape of a square. Okay, there are basically 500 turns. There are basically 500 turns in that coil, and the magnetic field through it is changing. The magnetic field is basically changing. So, question is, how much EMF is being produced? By definition, we know EMF induced magnitude wise is d phi by dt. What is the flux? The flux is basically magnetic field into area, but I'll have to multiply it n times because there are 500 loops. So each area is A, so BA, 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 like that 500 times BA will come, because there are 500 such loops. So the total EMF, when you calculate, you have to multiply it by the number of turns. B is same? No, it is changing. A is same? Yes. N is same? Yes. So take A and N outside, because that are the rules of derivatives. So AN into dB by dt. Now I can solve this. What is A? Area. This is 10 centimeter. Basically it is 0.1 meter. So the area of the square will be 0.1 square. Number of turns will be 500. The rate of change of flux dB by dt is 1 Tesla per second. So won't this be just 5 volts, my dear warriors? Where is 5 volts? It is option D, D for doctors. Very good, Kailash. Very good. Awesome. Proud of all of you. Very good, Subhashini. Very good, Rania. Very nice. Very nice. Yes, Ritigna. So the idea over here was, remember that you can change the flux by any of the three methods, by changing the B, by changing the A, or by changing the angle. Here you have changed it by changing the magnetic field itself. So everything else were constants, so they were brought outside the derivative. Only take the derivative of the magnetic field alone, that's all. And that was already given, 1 Tesla per second. Let us try to solve this question. There is a graph which gives the magnitude of a magnetic field, okay, which exists throughout a conducting loop. Imagine there is a loop, everywhere there is magnetic field. But that magnetic field, though it is same everywhere, it changes with time. Right now it is this everywhere. After some time it is so much and everywhere. After some more time it is different value everywhere. So you can see initially it was 0, then rised, stayed constant, then decreased, and then finally collapsed to 0. Question is, where do you think the magnitude of the EMF, don't worry about minus plus signs, where do you think the magnitude of the EMF is more, where do you think it is less? I think this is based on the slope part. I just told you about the slopes. What does the slope tell you? What does the slope tell you? The slope tells you the EMF produced. Remember, the slope will be directly proportional to the EMF induced. But just take the magnitude of that slope. Don't worry about it, because I'm only interested in the magnitude of the EMF. Okay, so let's try to think about the slopes. What do you think is the slope in section AB? Post the answers in the chat box. A to B, what do you think is the slope? I think it is flat, it's straight. So what should be the slope? Shouldn't it be 0, my dear warriors? No, I don't think this answer will be D. It will be something else, I guess. Don't you think the answer for the slope will be just a big fat 0? I feel there is one more region where the slope is 0. I feel there is one more region where the slope is 0. Where is that region? From C to D, do you see this is also flat? Shouldn't this slope be 0? Shouldn't this slope be 0? So in AB and CD, both the regions EMF will be also 0. EMF will also be 0 because slope is 0. So AB should be equal to CD. AB should be equal to CD. I can see AB is CD here. I can see AB is CD here. CT no. DET no. So I think option A got eliminated and option C also got eliminated. Do you see that? Do you see that? Both these options got eliminated. Okay. Okay. Now let's see. Do you notice one interesting thing? Whatever is the slope in this part will be also the slope in this part because it is the same straight line. If this is slope S1, won't this also be S1 only? Because it is the same straight line. So how can the slope be different? So DE should be equal to ET. DE, D to E, EMF should be equal to E to T EMF. DE is equal to ET. I can see that here also and I can see that here also. Okay, so I can't eliminate from that. Now think and tell me, out of this and out of this, if I call this S2, if I call this S1, who do you think is steeper? Who do you think has more slope magnitude wise? In this much time, it went up this much. In so much time, it came down by this much. I think this is more steep. This is more steep. This is more steep versus if I talk about this is less steep. This is having less slope. Agree or disagree? Because do you see there are two intervals of time in which it is coming down. Here in one interval of time only you are going up. So what does that mean? What does that mean? This EMF B to C should be more than E to T. B to A or A to B should be more than sorry, not A to B. B to C should be more than D to T or D to C or E to T, something like that. So I can see the same thing happening in B option, and this BC is more than this. No, this is 0. This is the yellow one is 0. So okay, so don't bring it in between. 0 will be the least of them all. So this is the least, so that will be 0. So I would say BC will be the highest EMF produced. DE and ET will be medium EMF produced, not so much. And AB and CD will be exactly 0. So I think it should be option B. Yes, it is option B. Why this is not so? Because this is 0. How can this number be more than this? Because this is some positive value. This is a magnitude. How can 0 be more than 2 or 3 or 5 volts? Obviously 2, 3, 5 volts will be more than 0. So this ordering is wrong. Got it? Yep. Awesome. Rangaswamy, I'm not so sure, bacha. Watch the classes over here. You will find almost similar content. So you can definitely watch the NEET lectures in English. Okay. So I would recommend you to do that. Okay. Chalo. Moving on to the next question coming up on your screen. Here it is. A rectangular coil. Okay. Of so many turns, area so much, resistance is also given. The field changes at 1000 Tesla per second. Wow, crazy. Find the current in the coil. Remember I told you the logic to find the current. Current is EMF by resistance, Ohm's law basically. So first find EMF. Obviously, automatically you will come up with the current also. So in order to find the induced current, I'll have to take the induced EMF divided by the resistance. So 1 by resistance, induced EMF will be d phi by dt. So what I will do next is 1 by R. Flux is nothing but BA into N divided by dt. Now I know A and N are constant, so I can bring them outside. So B into N divided by R into, sorry, not B into N, A into N. Area is constant, number of turns is constant, divided by R into rate of change of magnetic field. So area, well, area is 25 centimeter square, so 25 into 10 to the power minus 4 into number of turns, it is basically 20 the whole thing divided by resistance. What is the resistance? It is basically 10 ohm into dB by dt, rate of change of flux, that is 1000. So basically 10 to the power 3. You can see this 0 cancels. So all you are left out with over here is 25 into 2, which is basically 50 into 10 to the power minus 4, 10 to the power 3 will make it 10 to the power minus 1. So I think it should be 5 volts. Sorry, not volts, my bad, amperes, because this is current. So 5 amperes is the current. 5 amperes is the current. Very good. Yep. Very good, very good, very good. No, it is not 50. You would have missed some 0 or you would have missed some power of 10. Okay, somewhere or the other. So that is the answer. So current is EMF by resistance. Sometimes, you know, they will also ask you the charge which has flown. So don't get scared if they ask you how much Q flows in the circuit, how much charge flows in the circuit because the flux has changed, field has changed. What you will do is, since you know current is EMF by resistance and EMF is nothing but rate of change of flux per unit time, this current, write it as charge per unit time. So I will get this as 1 by R del phi by del t. Now del t and del t cancels, so the charge which flows will come out to be change in flux by the resistance. So if there is a question where flux change is known, resistance is known, you can easily find how much charge has gone or flown in the circuit. Because I know current is charge per unit time, time and time just gets cancelled. So that is also a possibility. Let's go to the next question coming up on your screen. This is an AIPMT PYQ question. So get up, buckle up, all your swords out. The magnetic flux linked with the coil satisfies the relation flux, not theta, this is flux. Okay, 4t square plus 6t plus 9 Weber, t is in second. How much EMF is induced at 2 seconds, magnitude wise? Come on. Rangaswamy, please don't spam, bacha. Okay. Watch it here. That's what I am saying, Rangaswamy. Watch those same lectures over here. I had completed exactly till whatever was done in the last lecture. So you can continue from this lecture over here. I will come back whenever time permits. For now, I am completely occupied. Honestly, if I could, I would have definitely taken the classes on JEE Conquer English batch, right? Okay. So, Pavish, you will have to join the Telegram channel. There is a Telegram group. Please join the Telegram group. There you will get the complete PDF. 22, is that so? Let's see whether you guys are correct. Wow, you would have cleared AIPMT here. Amazing. So because flux is known EMF, which is d phi by dt, just take the derivative of that. So just take the derivative of 4t square plus 6t plus 9. So derivative of 4t square will be 4 into 2t, 6t's derivative will be 6, plus 9 is a constant, so derivative is 0. So this will be 8t plus 6. But the question is at 2 seconds. So the EMF at 2 seconds will be 8 into 2 plus 6, which is 16 plus 6, which is 22 volts. Wow, beautiful. Understood? Clear? Very good. Very nice. Proud of all of you. Next question. This was NEET 2019. How many of you are going to conquer NEET 2019 if you went back in time? Let's see. 800 turns coil has area, okay, effective area, this much, is kept perpendicular to the magnetic field, and this much is the magnetic field. When the plane of the coil is rotated by 90 degrees around any of its coplanar axis in 1 second, the EMF induced in the coil will be, okay, so think about it. There is a coil like this. So the area vector will be in this direction. It is rotated by 90 degrees. That means the area vector will now turn over here. So earlier, all the field lines were cutting through it. Now, none of the field lines will pass through it. So here, the magnetic flux will be 0, finally. And here, I would say the magnetic flux here would be just B into A into cos of 0 degree. Cos 0 is 1, so it is just BA. Here it is 0 because cos 90 is 0. So the flux has changed. How much did the flux change by? How much did the flux change by? BA minus 0. So it is just B into A. So for the EMF, what will I do? The change in flux divided by the time. So the change in flux is BA divided with time. Okay. So what is B? B is 5 into 10 to the power minus 5. What is area? Area is basically 0.05 or 5 into 10 to the power minus 2. What is the time? The time taken is 0.1 second. That means 10 to the power minus 1. Now, if you look at this, there is something missing in this, and the something missing is the number of turns. Something missing is the number of turns. So I'll also have to multiply it with n. I'll also have to multiply it with n because there are n number of turns over here. So do not forget that n value. So when I multiply it with the number of turns, which is basically 800 over here, I will get the final answer. So what are you guys getting? Yes, very good, Srinath. Yes, the number of turns. B or something else. What are you getting? Come on, do the math. It's not very difficult. 5 5s are 25, 25 8s are. It should be 0.02 volts. Just check this out. 25 is 200, so it will be 2 into 10 to the power something only. So it should be 2 into 10 to the power minus 2 volts. Just check that out. Everyone with me on this? Everybody is getting option C. C for Captain Shreyas. Very good. C for Capto. Very nice. Very nice. Perfecto. Let's go to the next question. This is a NEET 2013 question. A wire loop is rotated in a magnetic field. The frequency of the change of the direction of the induced EMF. See, in that previous question, the loop was rotated by 90 degrees. So imagine the loop is rotated continuously. So how will that EMF change? Think about it. So there is a loop. There is a loop and it is basically rotated. So if it is rotated in that field, the frequency of the change of the direction of the induced EMF. Now, why will the induced EMF change the direction? Because once the flux will be increasing, once the flux will be decreasing, increasing, decreasing, increasing, decreasing. So, in one rotation, think about it, in one rotation, the direction would actually change 2 times. Yes, not once, 2 times. Be careful. Because from here till here, it would change the direction once. And then from here to back to here, again it will change once. Every half revolution, it will change the direction. Every half revolution, it will change the direction. So it will be twice. If you don't believe me, no issues. I will prove it to you. That will be easier. Imagine there is a coil. Imagine that there is a coil and there is some area vector and there is number of turns, and let's say the magnetic field cutting through it is basically B. So there is some angle also covered over here, theta. Because that particular loop is rotating with an angular velocity omega, in time t how much angle will be covered? In time t how much angle will be covered? Angle covered will be omega into time. Because angular displacement is angular velocity multiplied by the time. Now, if I ask you what is the flux is BA into N. This is the flux BA into N, but into cos of theta. Because the area vector and B vector, they are not in the same direction. There is an angle theta between them. That theta will keep on changing as the coil will rotate. As the coil rotates, the angle will also keep on changing. Understood, my dear students? Okay. So what will be the EMF? Which will be d phi by dt. So it will be BAN. All these are constants. So bring it outside. Only take the derivative of cos theta. Because theta is changing. It is not constant. Now substitute the value of theta. So it will be derivative of cos omega t. What will it be? Derivative of cos omega t. So what will be the EMF? Think about it. BAN. Derivative of cos. What is the derivative of cos? It is minus sign. So minus sign omega t, correct? But since omega is getting multiplied inside, do not forget to bring that omega outside also. That comes via the chain rule. How many of you remember it? Very good. So when sin x's derivative is asked, it will be cos x. But sin alpha x's derivative will be cos alpha x into alpha. That alpha will come outside. That multiplying factor comes outside. So basically the EMF is minus BA omega n sin omega t. Basically this is a sine graph, yeah, but a minus sign because that minus is there. So if you look at it graphically, it is like this. This is one revolution. This is one revolution. I hope you can see that. This is exactly one revolution. So if you notice, in one revolution, the direction changes here and then here, or if you don't count this, then here and then here. So either you include this or you include this. Don't include both, or else you will be like, sir, it changes 3 times. Okay, don't do that. So if you start the time after this, just after this 0, so after 0 if you start it, it has gone from negative to positive, and then when it just reached here, it went from positive to negative. So it basically changes 2 times in one revolution. Did you see that? Understood, my dear students? Okay, I hope this is clear. Everybody with me? This is a very, very important question. Many people ignore this question thinking this is a just theoretical question or statement question, or they try to by heart it. Don't try to by heart it. Think why it is 2 times. So in one complete rotation, there is an increase to decrease and again decrease to increase. So in one complete rotation, it changes 2 times, my dear students. Okay, perfect. Let's go now to Lenz's law. Now that you are, very, very conceptually strong, or at least the basics are clear about Faraday's law. Now, what is this Lenz's law? See, Faraday's law told me the magnitude. So, what did Faraday's law give me? Faraday's law basically gives you the magnitude of the induced EMF. The magnitude of the induced EMF. But what about the direction? So that is exactly what Lenz's law gives us. Lenz's law gives you the direction of the induced EMF. The direction of the induced EMF. Now, how does it give the direction? The logic is, in Lenz's law, by energy conservation. Energy can neither be created nor can be destroyed. So energy conservation. So think about it. If there is electricity generated in anything, there must be something which is losing. There must be some other form of energy which is losing somewhere. So always energy is conserved, no matter which part of physics you go, be it optics, modern physics, mechanics, thermodynamics, anything, even in magnetism. So if one form is created, other form is destroyed, but the total energy is remain conserved. So if electricity is being generated, right, it will always try to oppose the change of the flux in such a way that the total energy remains conserved. Because if it does not oppose the change in flux, meaning, just imagine you take a magnet. Just let's go back to this particular simulation. Imagine I take this magnet, and if I were to move it like this coil will oppose or repel the magnet. It will be like, hey, stop. Why does it stop? It is just like how it is in your house. Imagine you are this magnet, this is your house, all the elders in your house. If you say, I want to go out to play, they will be like, no, go back and study. If you say, okay, I will go back to study, they will be like, come, why are you only studying? Come play. If you say, okay, I will go for a party, what is this? Don't go for the party. If you say, I will not go for the party, they will be like, why are you not going for the party? Go for the party. What are you doing sitting at home? Everything oppose. Everything. If you do this, no. If you don't do that, why are you not doing that? Okay, so that is what Lenz's law is. It will suck out that energy. Think about it. Or else, magically you could have created so much of energy. I throw this magnet, the magnet gets attracted. Zoop. So it will generate more and more electricity. The magnet is getting more and more kinetic energy. Wow, party is happening. Magnet is also getting energy. Electricity is also being generated. Who is paying for all this? Who is paying for all this? Nobody. So where is energy being created from? Nowhere. So it is violating the conservation of energy principle. So if electricity is generated, magnet will lose its kinetic energy. Magnet will lose its kinetic energy. So if it was going fast, it will slow down. If you throw it like this fast, it will slow down because it will lose its kinetic energy, and that kinetic energy gets converted into the electrical energy, my dear students. So always that opposition is there. Keep that in mind. So according to this law, the change, or basically the induced EMF always opposes the change of the flux. Let's take some examples so that you understand what I mean. Okay, so let's understand what do I mean by this. So imagine that I have a coil. Okay, I have a coil and there is magnetic field inside of it, and let's say the magnetic field is going inside the plane like this. Okay, it's going inside. So the magnetic field is inside. Let's say it is increasing. What is happening? It is increasing. Now, because it is increasing, isn't the flux changing? So won't, by Faraday's law, there will be electricity created? In what direction will the EMF be created? Clockwise or anti-clockwise? So think about it. EMF is being induced inside. EMF, or rather I would say magnetic field is increasing in the inside direction. Magnetic field is increasing in the inside direction. So what will you say? No, I don't want that increase. You will oppose it. It is becoming more stronger inside. You will be like, no, I want to make it weak. So what will you do? You will create an induced EMF, induced field outside. So the induced magnetic field will try to oppose that change. How do you create a magnetic field this way, out of the plane? Hold your thumb towards this direction, outside the plane. Do you see your fingers crossing like this? Right? Curling like this. So what is that direction? That is anti-clockwise. So the induced EMF or the current will be in this direction. So this is how the induced EMF or the induced current would be. Understood, my dear students? Magnetic field is increasing. So to oppose, you will create an induced EMF. Induced field. Induced field will be this way. So to create a field this way, hold your thumb in the field's direction. Automatically, the curled fingers tells you the direction of the current creating the field. Imagine the same situation, but this time, imagine the magnetic field. Imagine instead of increasing, imagine it is decreasing. What will you do now? Oh, Papa, the field is decreasing. Let me help it. The Papa field is decreasing. So what will I do? I will help the field by creating an induced field in this direction. If I induce the field inside to help it, because it is decreasing. If it decreases, I will try to help it. If it increases, I will try to put it down. That's how it is. Oppose. So hold your thumb inside. The fingers will automatically curl in this direction. So hence the induced EMF or the current will be in the clockwise direction. Is that absolutely clear in everybody's mind? Absolutely clear in everybody's mind? Cool. Similarly, my dear students, imagine that you have a coil. Okay, you have a coil and you have a magnet. Let's say this is the south pole, let's say this is the north pole. Now imagine somebody happens to move the magnet here. Okay, somebody happens to move the magnet here. So let me also show the axis. This is the axis. Okay, somebody tries to move the magnet here. Don't you think electricity will be induced in the coil? Obviously, I just demonstrated that to you in the animation. Obviously, there will be current which is created, EMF which is being induced. Perfect. So now think, what will be the direction? Will the coil push it away, or will it be like, hey, stop, stop, stop? The moment you go away, it will try to stop it. It will try to pull it. If it tries to come towards you, it will try to stop it again by pushing it. Whatever you do, it will try to oppose. How do you oppose? By attracting it, because it's going away, right? Attract it. How do you attract it? So you create a current which creates a magnetic effect to stop it, to attract it. So basically make the north pole here and south pole here. So this coil behaves like an electromagnet with north pole here and south pole here. This north pole will attract the south pole. This north pole will attract the south pole. How do you create these induced poles? How do you create these induced magnetic poles? Come on guys, if the magnetic poles goes from south to north in the right direction, hold your thumb also from south to north direction. South to north direction. Do you see your fingers curling like this? The fingers are curling like this. So hence the current will go in this direction. This is how the EMF or the current direction will be. Is that absolutely clear? So that is your basically anti-clockwise direction. Needless to say, if imagine this was the coil, and the same magnet, this was south, this was north. Okay, this same magnet was now made to move like this. What will this coil say? The coil will be like, hey, don't come near me. Stop, 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 stop. It will try to repel it. How do you repel? By obviously creating like polarities. So now this will be south, this will be north. See, this was south, this was north, south, north. Now it has become north, south. Understood? So how do you create these induced magnetic polarities, my dear warriors? Go from south to north. The magnetic dipole is like this, south to north. The curled fingers are in this direction, like this. So the induced EMF or the current will be in this direction. That's how Lenz's law works. Understood? Is that clear? User phone, you can watch the lectures here also. No problems. Okay? Perfect, perfect. Awesome. Very good. Very good. So, combining both of them together, I can always say that the induced EMF, not magnitude wise with the sign, will be negative d phi by dt, Here, this derivative term comes from the Faraday's law, and this minus sign comes basically from the Lenz's law, just to say that it is opposing. But don't worry about the minus sign, because that minus sign is not going to take you anywhere. It will hardly help you. Just like in spring force, hardly that minus sign helps you, because you have to decide the direction with logic than the minus sign. What is important is these kind of questions where they will give you a coil is changing area, or the field is changing, or a magnet. What is the direction of the current? Correct? So based on that, you will have some tricky questions to try to solve them. Don't worry, we'll get some practice now with these questions. Some of them are PYQs also. So stay tuned on the channel, guys. If you have not yet subscribed, please subscribe. It's very important, or else you will miss these classes, because this is the only NEET English channel in the country which is regular, which is going to give you quality content with the best teachers. There is no other channel that you need after this. Okay, and I hope you are extending your support and talking about this channel to your batchmates, to your schoolmates. Wherever you go, you should talk and feel proud about this channel, because this is a channel for you. Keep this in mind. So Lenz's law is based on the principle of conservation of. This was asked in JIPMER 2019, and I can see all the students giving the answer. B for banana, very good, energy. So it's based on the conservation of energy, so you cannot violate it, or else you would see magically new energy being created. So always the flux change is opposed. Great. Lenz's law gives the direction of the induced current, magnitude of the induced EMF, magnitude of the induced current, magnitude and the direction of the induced current. Very simple question, just play with the words. Just the statements are confusing, that's all. Okay. Triveni saying A, Subhashini saying A, Praveena saying A, Kanshi saying D. Is that so? You guys like the word D, D for doctor, but it is not D, it is A. A for Ames. A for Ames is the answer, my dear warriors, because Lenz's law, I just told you right over here also. Minus sign gives me the direction. In fact, at the beginning also over here, I told you. Lenz's law gives you the direction of the current or the EMF. Faraday's law only gives me the magnitude. That's how it is. So bear that in mind, keep that in mind, very, very crucial. Simple concept, simple facts. Next, there is a ring which is horizontal. There is a magnet which is dropped from the ring above it. Then the ring the magnet falling inside the ring will have an acceleration equal to g, less than g, more than g, depends on the diameter of the ring. Think about it. There is a ring, that means it can carry some current, and you have a magnet over here. It could be north, it could be south, it could be anything. If you drop it, what do you think the acceleration will be? Will it be equal to g, or will it be more than g, less than g, or it depends on something else only? Come on, my dear students. Very, very simple question. What do you think will happen? If I drop the magnet, the flux will change. The flux, because there will be some field lines definitely cutting through. The flux will change. The flux changes. So because of that, there will be induced EMF. Because of that, there will be induced current. Because of that, there will be induced field, and that will oppose the motion. That will oppose the motion. So, meaning apart from the weight, which is mg, there will be some repelling force. It will be repelled by this coil's current, and hence the acceleration will be less than g. If only mg was there, it would be g. Because there is a repelling force, it will be mg's minus something will be the net force. So it will be slightly less than g. Option B. Very good. Very good, Kailash. Very good, Prabha, Suhasini, Vedanjani. Some of you made a mistake thinking that it depends. No, it does not depend. It is just going to be opposed. So that's why it will not do a free fall motion. So this is not a free fall. Not a free fall. Because for a free fall means the word free says there is no other force apart from gravity. But here there is a force. So hence it is not a free fall motion. Keep that in mind. Moving on to the next question coming up on your screen. North pole of a bar magnet is moved towards the coil along the axis, passing through the center of the coil, perpendicular to the plane of the coil. The direction of the induced current in the coil when viewed in the direction of the motion of the magnet. I just made you solve a question like this, just that the diagram was given there. Here you have to visualize. Draw the diagram and figure out the direction. Yes, Niranjan will be starting with the 11th standard remaining topics till Newton's laws, friction, and I think some of the things over there, work, power, energy, we have completed. Okay, 11th standard topics are completed. Remaining chapters like center of mass, etc. I'll be starting after a week. Okay, so be prepared for that. We'll be doing the 11th standard topics. The correct answer for this is anti-clockwise direction. No. Many people are saying clockwise. Let's figure this out. The north pole of a bar magnet is moved towards a coil. Okay, so this is our coil. Okay, so this is our bar magnet. This is the north pole. This is the south pole. The bar magnet is being moved like this because the motion is towards the coil. Okay, along the axis towards the coil. Perfect. So what will happen? There will be induced polarities inside the coil. The north pole will repel the north pole. The south pole will be here. So in order to create this polarity, you will have to hold your thumb from south to north. That's how the magnetic dipole moment will be. So you will see that the curled fingers will go like this. It will go like this. So it is going in this peculiar manner. So if you see from here, what will you see? You will see it is going in anti-clockwise direction, which is option B. Very good. So that's why option B. See, obviously C and D you will not write. You are that smart after studying Lenz's law. You will be only confused between A and B. But that confusion is very important, that you have to clear it. If you are like, oh no, clockwise is wrong, okay, then it will be anti-clockwise. Don't do like that. Think why it is anti-clockwise or clockwise. So because the whole game is only whether it is this or that. I mean, just those two options. So that is the main theory. Don't be so marks oriented while learning the concept that, oh, if it is not A, it will be B. Oh, if it is not B, it will be A. No, don't study like that. That is a wrong way of looking at it. Next question coming up on your screen. There is a magnetic field perpendicular and into the plane of the paper. There is some random irregular shape. It is slowly changing into circular loop. Then what do you think will happen? So imagine this to be a random shape. Okay, slowly it is becoming, okay, into a circle. Slowly it has transformed itself into a circle. So think about it. In this process, what do you think will happen? Will the current be anti-clockwise, clockwise, etc.? So what is it? The magnetic field is perpendicular and into the plane. So the magnetic field is basically like this. Think about it. What do you think will happen in this case? Sir, why we didn't take north-south? Pravina, because magnetic dipole moment is like that. That's how you find, that is the right-hand rule to find the direction of the field. So when the current goes in the direction of the fingers, then the thumb points in the direction of the polarities from south to north for a magnetic dipole. So that's the thumb rule, the right-hand thumb rule. Okay, and south to north is always taken as the convention for the magnetic dipole. Okay, cool. So what do you think is the answer for this, my dear students? Think about it. Okay, fine. Isn't the area changing? Here the area is less, slightly more, because if it was some irregular shape, if you try to pull it and make it into a circle, what are you trying to do? You are trying to expand, because circle is the maximum area for a given length. For a given perimeter, you cannot have a figure more area than the circle. Keep that in mind. So I can just say from here to here, this had less area, this has more area. That means this has less flux. That means this has more flux. If the flux has increased, what will you do? By Lenz's law, you should oppose that increase. How will you oppose the increase? Check. How is the flux going? Inside. How will you oppose? By making it go outside. Oppose it by creating an induced field. Oppose it. So this is the induced field. The induced field will oppose the increasing flux. So hold your thumb outward. Hold your thumb outward. That's it. Do you see your fingers going this way? Your fingers going this way? That's it. So this will be the direction of the induced current. So it is basically in the anti-clockwise direction. Anti-clockwise direction. Option A. I have seen many teachers and many books trying to give you some stupid tricks for remembering the directions. Okay, they try to show this, some north and south, and if it is going away, then it is like this. If it is coming towards, then I don't know, something like this. So some crazy things they try to do. Don't do like that. It is very simple. Always see whether it is increasing or decreasing. If it is increasing, try to weaken it. If it is weakening, try to strengthen it. That's all. And you should just use your right hand rule. That's all. South to north. Thumb goes south to north. The fingers goes in the direction of the current. That's all you need to do. With little bit of practice, this will be like a simple thing to do. You will do it within 20 seconds. Next question coming up on your screen. Check this out. Very beautiful question. These are not two triangles. This is the same loop, but it has been twisted. Okay, just try to think about it. It is like this, and there is a jump over here like this and like this, something like that. Okay, it is not joint. Try to visualize it. Question is, if the magnetic field is increasing, so it is clearly mentioned in this problem, this magnetic field is increasing, then what is the direction of the current in AB part and CD part? Basically, try to figure out how the current goes, then we can figure out in AB, CD or any other such wire length. Okay. Now, tell me one thing. Out of this triangle and this triangle, triangle AB, maybe we can mark this particular point as, let's say, E. ABE versus EDC, which triangle is bigger? Which triangle is bigger? Come on, my dear students. Which triangle has more area? Just tell me that first, then we'll go ahead. Obviously, triangle ECD is more than triangle ABE. So if you take the entire loop, for the entire loop, since the triangle ECD is bigger than triangle AEB, so if each triangle gives me the direction of the EMF by Lenz's law, whose effect will be more dominating? This triangle, let's say, gives one direction, this smaller triangle gives me some other direction, just giving you an example. Whose effect will be more, bigger one or smaller one? Obviously the bigger one, more area, more flux, more EMF. So this is the more dominating one. So everything you will find it direction wise with respect to the bigger triangle, understood? So just concentrate on that bigger triangle. Okay, this is E, this is C, and this is D. If the field is increasing inside, by Lenz's law, what should you do? You should oppose it. You should oppose that increase. So the induced field, what will be the direction? Obviously it will be towards you. The induced field will be towards you. So if you hold the thumb towards you, see how the fingers are curling. It is curling anti-clockwise. That means it will go like this. Understood? So it will go from D to C. So if it goes from D to C, it will also go from C to E. It will continue. It will go from E to B. Then it will go from B to A. Then it will go from A to E. Then it will go from E to D. And then it will go from D to C. So that is how the current will go. Because it is one wire. Obviously the currents can't be going in both the directions. That will be stupidity. So hence answer is B to A and D to C. Beautiful question, guys. Diya, we'll be starting it after some time, after we do waves. There will be a pause because we'll be doing some 11th standard topics and maybe ray optics and all of that. And after that, we'll be doing your AC. Because you will understand AC very easily once you study SHM and waves. So I want to do those topics also. Cool? Chalo. Let's go ahead to the next question coming up on your screen, guys. Here it is. Two similar loops carry equal currents. In the same direction. On moving the coils away, the current will what? Will it increase or will it decrease? Okay, let's try to understand. There is one coil over here and there is another coil over here. What are you trying to do? You are moving them away. So you are pulling them apart. Okay, so either you move one or you move this or you move both. One and the same thing. You are moving the the coils further apart. The electric current will increase in both, decrease in both. What do you think will happen? The moment you show the currents, I think things will become more apparent. Let's say the current is going like this. So using your right hand rule, if the current actually was going like this, then your thumb will point towards the right side. the thumb will point towards the right side. So I think this should be the north pole, this should be the south pole. This should be the south pole, this should be the north pole. Everybody agrees with this? These will be the polarities of both the electromagnets. Are these two electromagnets attracting or repelling? Just tell me that in the chat box. Are they attracting or are they repelling? Just tell me that much. That much is enough for me. Then I will tell you what to do next. Think about it. This is south-north. This is one bar magnet, like a bar magnet. This is one north-south, another bar magnet. Will these two magnets attract or repel? Don't you see north and south will attract? They are close. Definitely attract. Okay, that was clear. Now, when you move this coil away, when you actually move this coil away, according to Lenz's law, what should happen? You will oppose the motion. You will oppose the motion. So, basically, you will oppose it by what? Attracting it. By attracting it. And how do you attract it? How do you attract it? Make both the magnets stronger. Make this magnet strong. Make this magnet strong. How do you do that? By increasing the current. By increasing the current, the magnets will become more polar. They will have stronger magnetic properties, electromagnets. So that's how you end up attracting them. Hence, both of them will have increase in the current. Both of them will have increase in the current. Is that clear? It's such a simple way to look at things. There is no complicated sign convention. There is no complicated maths. And do you realize that all those people who learn this minus d phi by dt, this minus sign is pretty much useless. Not even in one single question till now we use that minus sign. If there is a proper question where the flux is given and you have to give E with the sign, that's okay. But all these questions, what is the use? Okay, fine, it is minus. What do you do with that? Nothing. So it's all about using the right hand rule. So don't worry about the minus sign, guys. That's what I've been telling you. Focus on how Lenz's law works, how the right hand rule works, whether it will strengthen, weaken, increase, decrease. That's the logical part you have to build. Understood? Everybody with me? Clearo? Awesome, 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 awesome. Chalo. Let's now slowly move towards motional EMF. Let me just drink some water. Okay. Till now, what did we see? Faraday's and Lenz's law, and we saw that whenever you change flux, there is electricity created, and there are different ways of creating the flux. By changing the field, by changing the area, or by changing the orientation. Now, we'll see, actually it's Faraday's law only, but looked at it in a slightly different way, where you take a conductor and move it inside a magnetic field. You take a conductor and move it inside the magnetic field, electricity is created. So, for example, imagine you take a rod of certain length. Okay, so this is a conducting rod, and let's say, there is some magnetic field like this. There is some magnetic field like this, and let's say you end up moving this like this. Rod is somewhere, velocity is somewhere, magnetic field is somewhere. You will see that the rod will actually behave like a battery. Like a battery, there will be some induced EMF. It will behave like a cell. There will be some polarities which will be created in it. Because the rod is moving, hence the word motional. Because it behaves like a battery creating EMF, hence the word EMF. That's why the words motional EMF. A moving conductor in the environment of a magnetic field induces EMF, behaves like a battery. That's why the EMF produced is called as motional EMF. Right now, there is no current. Right now, if you ask me, there is obviously no current in it. But you can even create or see that current if you connect it to something. For example, imagine this is a rod. Imagine these are two rails. Imagine these are two rails and there is a bulb over here. Imagine there is a bulb over here. If now you start moving this rod with some velocity, and imagine that there is some magnetic field over here. Imagine that there is some magnetic field over here. You will see that this rod will behave like a battery. There will be induced EMF, but now there is a conducting path. Now there is a conducting path. So definitely you can think of it as if it's like a battery. It's like a battery which is now connected to a bulb. So there will be induced EMF, but also you will see some current in it. Also there will be some current in it. So in that case, because nothing was connected, what will current do? Where will it go? Nowhere. So there was no current. But the moment you create a conducting path, there is a current flowing apart from the EMF. Hello Ekibala. Did you guys understand this concept? When EMF, when current, when no EMF, etc. Okay. So how much is this EMF created? Let's find that out. Let's see the formula for that. The formula for finding the EMF, a lot of people give crazy formulas. I won't hit around the bush. I will give you the direct actual formula, because a lot of people say, oh, when length is in the direction of velocity, no EMF. When length is in this direction, then sine theta. Then when B is in this direction, then no EMF. No, I won't give you cases. I'll give you the basic direct formula which will help you in every case. Godfather formula. So the induced EMF is given by L vector dot V cross B, and the polarities, or basically the direction of the EMF is in the direction of velocity cross magnetic field. This is the only formula that you need to know. Everything else will follow. Electric EMF, the electricity induced, which is the EMF induced, will be L vector dot V cross B. L is the length vector. So you usually choose the length in a very simple manner. Wherever the rod is, you will choose the length vector in the same direction. Okay. So let me show you some examples so that you actually understand it. Okay. So let's take a rod like this. Then let's take a rod again like this. Then like this, then like this. Okay, so in each case, let it move in different directions. Here it is moving like this, here it is moving like this, here it is moving like this, here it is moving like this. Okay, then field also can have different directions. Here the field is like this, here the field is like this, here the field is like this, here the field is like this. Okay, then so many other possibilities are also there, guys. Magnetic field is perpendicular or in the direction of velocity. So many cases. Let's just understand these basic cases at least. Remember the formula. The formula is induced EMF is L dot V cross B, and this is which gives me the direction of the EMF. Now look at it one by one. V and B both are in the same direction. So what will be the direction? What will be V cross B? Cross product of two parallel vectors. Angle is 0. Sine 0 is 0. Sine 0 is 0. Yes, that's what I'm going to teach you. How to find which side is positive, which side is negative. That's exactly what I'm teaching. So what will happen? Won't the value of V cross B be 0, guys? Won't V cross B be 0? So what does it mean? No EMF will be produced. No positive, no negative, no EMF only. Understood? Very good, Priyanka. Very good, Pramina. Hello, Rupesh. Good evening. Next, let's go to this one. V is like this, B is like this. If you do V cross B, V is like that, B is like this. Hold your right hand in the direction of V, then B. The curled fingers go from V to B. Where is the thumb going? Inside. So I think V cross B is inside. V cross B vector is inside. Do you see the length vector in this direction? The length vector in this direction. So you have to take the dot product of this vector with this vector. Length vector is here. V cross B vector is inside. V cross B vector is inside. Length vector is this side. What is the angle between them? What is the angle between them? 90 degree. So cos 90 is 0. When you take dot, it is cos. When you take dot, it is cos. So cos 90 is 0. So what will happen? Again the EMF induced will be 0. The EMF induced will be a big fat 0 because cos 90 is 0, because V cross B is perpendicular to the length vector. So this is perpendicular to this. Understood? Clear? Awesome. Very nice. Very nice. Awesome. Next, let's go over here. V is parallel to B. Gone. The moment V is parallel to B, don't even bother. V cross B 0, 0 into donkey 0, 0 into monkey 0, 0 into length 0. So hence the induced EMF will be big fat 0. Here, V is like this, B is like this. How will V cross B be? V like that, B like this. V cross B will be inside. Just like over here, V cross B will be inside. Where is length? Length is again over here. Length is again over here. Length is up. V cross B is inside. Don't you see the angle between them? V cross B is inside. Length is upwards. Don't you see that they are actually perpendicular to each other? So again, don't you see V cross B is actually perpendicular to the length? So what will be their dot product? What will be their dot product? Cos 90 is 0. Cos 90 is 0. Hence, the induced EMF is again 0. Got it clear? No teacher will teach you with all these cases. I'm pretty sure very few teachers in the country actually take up these cases, because you try to by heart some things. You cannot by heart these cases. How will you even remember this in the exam is beyond my imagination. Okay, so when do you think then some good EMF will be produced? Well, let's see. What if my length is like this? This is my length vector, and okay, this is my length, and let's say the velocity is, let's say, in this direction, and let's say the magnetic field is inside. All three are perpendicular to each other. Wow, crazy. Velocity is right, magnetic field is inside. From right, it has gone inside. See where the thumb goes. It goes up. V cross B has just gone up. Very good. So this is the direction of V cross B. Best part, it is parallel to the length. Best part, it is parallel to the length. So cos 0 is 1. So thankfully it is not 0. Thankfully the value of cos is not 0. So hence the EMF induced will be L, V and B. L into V into B. That's it. Everything is 1. Anything into 1 is that anything only. So hence this is the EMF induced. But what is the direction? What did I tell you? V cross B gives you the direction. That means the polarities are like this. This is positive, this is negative. This is how the EMF is. This way. Exactly. Replace this with a battery pointing up. So hence this will be the positive polarity, this will be the negative polarity. That's how you get polarities. Is that clear? Absolutely. Clear, everyone with me? Shall we take one more example so that it is absolutely clear in everybody's head? Imagine the length is like this. Imagine the velocity is, I don't know, somewhere else. Velocity is somewhere else. Okay, and let's say the magnetic field is towards you. The magnetic field is basically towards you. Some random directions I have taken. Can you quickly figure out the polarities on your own? Velocity is right. Velocity is right. Magnetic field is towards you. If you basically are seeing the screen, velocity is towards the right, magnetic field has gone behind you like this. Okay, so V cross B will go up. Notice that first thing, V cross B will go up. Perfect. So replace it with a battery like this, but actually the length is not in this direction, it is in this direction. So there will be basically a component of that battery, you can think like that. There will be a component in this particular direction. So this would be the positive polarity, this would be the negative polarity. It will not be 0. Even if the length makes an angle, it is okay. Even if the length makes an angle, it is okay. This angle is not 90, na? So cos theta won't be 0. So EMF also won't be 0. Keep that in mind. EMF also won't be 0. How to find the angle between the area vector and the field vector? Area vector, you can always draw a perpendicular to the surface. Imagine the surface is horizontal. If you show a perpendicular, that's it. It's this way. If the area is the plane of this board, I can show a perpendicular. That's it. Always take the angle between the perpendicular drawn to the surface and the actual field. That's all. That's how you find it. Cool? Okay. Okay. Awesome. 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 Let's move ahead. Let's move ahead to some more properties. Now, imagine a situation where you don't have a straight wire, but instead you have a curved wire. This is a curved wire which is translating. Okay, maybe it is moving with some speed like this. Maybe there is some magnetic field like this. To find the EMF might be a crazy thing to do because each part is in different directions. But if this magnetic field is uniform and it is translating as it is translating, not rotating, it is translating, then you can easily find the EMF induced in it. All you need to do is take this point, take this point, take this point, take this point, and just draw a straight wire. What you will do? Just draw a straight wire. This will be the effective length. What will this be? This is basically your effective length. Now solve the problem as it is. Just keep the same velocity, same direction. Just keep the same velocity, same direction, same magnetic field. That's it. You will get the answer. So basically, whenever you have a curved wire, you can replace it with a straight wire and you can solve the problem. Something like this. Just imagine there was a semicircle, okay, of radius, let's say r, and let's say this semicircle was moving like this with some velocity inside some magnetic field like this. If the question asked is how much EMF is induced, what you will do first is convert that semicircle into a straight line joining the end points. So if you join the end points, it will just look like this. The length will actually be the diameter, which is 2r. R plus r will be 2r. Everybody agrees? Okay. How is the velocity? The velocity is in this direction. How is the magnetic field? The magnetic field is inside. Okay. V cross B. V cross B is like that. Check that out. V cross B is upwards. V cross B is coming out to be this direction. Velocity is there. Magnetic field is inside. V cross B is up like that. So it is actually parallel. It is actually parallel to the length. So therefore EMF is definitely not 0. In fact, the EMF will be LVB. Here the length will be 2R. So 2RVB is the answer. 2RVB is the answer. Understood, my dear students? Yep. If you ask me the polarities, obviously this will be minus, this will be plus. So this will be minus, this will be plus, because this actually behaves like a battery in this manner. This will be the EMF. This is minus, this is plus. So that's how you do these kind of questions. So anytime you see a curved wire, convert it into a straight wire, it becomes a simple question. Okay, so this property is very, very important. So I am putting a star mark over here. This is a very important property. Now, there is one more thing, one more formula which you need to remember for a rotating rod. So, the EMF in a rotating rod. What do I mean by that? Imagine this is a rod, okay, and it is rotating like this with angular speed omega. and let's say there is some magnetic field also like this everywhere. Okay, there is magnetic field like this. This rod, although it is not translating, will still have EMF in it, because each part of the rod is moving. So there will be a motional EMF. 100% there will be a motional EMF. So if you take any small part of the rod which is at some distance from it, it will have some velocity. If you take the next part of the rod, it will have some more velocity. If you take the next part of the rod, it will have even more velocity. How do I know that? Because velocity is omega into r. Omega into r, right? More the distance from the center, more is the tangential speed. So can I say then, if I have converted this into this problem, each part is going to behave like a small battery. There will be a small battery here, then another small battery here, then another small battery here, like that from the center till the end. From the center till the end. Do you see that? Small EMFs. Each part has some EMF, and each EMF is also different. Each EMF is also different. So if I combine them into one single battery, with total EMF E, that total EMF E will be integration of all those small EMFs. The formula which comes out after integration is half B omega length square. This is something which you have to remember, my dear warriors. Okay, so it comes after integration from this end to the other end. So you have taken the rod and divided into small parts, each moving with different speeds, each producing different EMFs. So you add all the EMFs in series, you get the total EMF. As simple as that. Okay, these kind of questions can also come. Sometimes the questions can be also very interesting, something like this. Imagine there is a rod like this, and it is rotating about this point. This length is L, this length is 2L. Crazy question this is. There is magnetic field here. Question is, what is the EMF induced between these 2 points? This point and this point. What is the EMF induced between these 2 points? That can be the question. The rod is not rotating about this point, be careful. It is rotating about this particular point with angular speed omega. This is L, this is 2L. Asymmetric. You know what you can immediately do? See, you can divide it into 2 parts. You can divide the problem into 2 parts. This is the pivot point, the center point here. This part is one rod, this part is one rod. This rod will have one EMF like this, I can call it E1. One EMF like this. This rod of length 2L will have another EMF like this. Obviously it will be opposite only. Obviously it will be opposite. If it goes from in to out, it will go from in to out everywhere. Correct? So these are the 2 EMFs. Oh, do I know E1? Definitely. It will be half B omega L square. Do I know E2? Yes, half B omega 2L square. So if I convert it into one single battery, obviously this will be the larger battery. It will look like this. And that will be nothing but E2 minus E1, which will be B omega L square by 2. Here 2 square is 4. Here L square means only 1. So 4 minus 1 is 3. So this will be 3 by 2 B omega L square. Think about it. That would be the net EMF in this. Excellent, Priyanka. So these kind of questions can also come on rotating rods. So now that you know how to do these problems, any kind of problem that will come in the NEET exam, I'm 100% sure you will conquer it. So you should know how to convert it into simpler problems. So we saw 2 simple conversions. One was curved wires to straight wires. That is one pattern of questions. Another pattern of questions is rotating rods. So you should know from start, from the pivot to the end, this is the formula. So if it is hinged somewhere else, you know what to do. Okay? Now, in motional EMF only, the last part is something called as the, eddy currents. So, eddy currents. Eddy currents. So, what is this eddy currents? Imagine you have a conductor. This is some conductor. Rod, disc, cylinder, sphere, whatever. Some conductor, and it is moving. It is in motion. But it is not in motion anywhere, it is in motion in magnetic field. So there is some magnetic field also. Magnetic field also. So the moment you move that conductor in the magnetic field, what will happen? Think about it. What will happen? There will be motional EMF. Motional EMF which is created. Because it is a conductor, within the conductor itself, you don't need something else from outside. Inside that conductor only, there will be a current loop which is set up. Agree? There will be a current induced in it. There will be current loop induced inside of it only. So, if this was your conductor, okay, whatever, this was your conductor, inside that only, maybe one is positive, one is negative, one is positive, you can get the positive negative signs with the cross product rule. So maybe the current is going to go like this inside of it, maybe the current is going to go like this inside of it. So you can see probably currents being set up inside of the conductor. So these currents are basically called as eddy currents. These are called as what? Eddy currents, my dear warriors. Is that clear? Everybody with me? These are called as eddy currents. They are random. They are in loops. They are inside the conductor. They are coming because of motional EMF. But they are not, not harmless. They are actually harmful. Basically, they take away something. They just don't come and chill out. Whenever current flows, what will happen? There is some resistance in the conductor. There will be some energy loss, heat loss, I squared R losses. So you will see, because of those currents, there will be I squared R losses in the form of heat. So you will see that energy is lost. Energy is lost. So this motion will be retarded. All right. So the motion is what? Retarded, decelerated because of these losses. Kinetic energy gets converted into heat energy. So now you might be thinking, sir, maybe it's not a very bad thing. I think I can use it. Where do you think you can use this? Is there some application? Can I use this somewhere? Think about it, my dear students. Put it up in the chat box. It's after all not such a bad thing also. I think we can use it for stopping some object. Maybe a car, maybe a bus, maybe a train. What if the rotating wheel, obviously it is made of metal, it is a good conductor. If I want to stop the train, instead of applying force, pressure, friction, which creates sparks, wear and tear, what if I bring a magnet close to it? The moment I bring a magnet close to the wheels of the train, what will happen? It is motional EMF. Motional EMF means eddy currents. Eddy currents means I squared R losses. Heat is generated. That's it. The energy of the kinetic energy of the train gets lost as heat, and you are stopping the train. So you can have retarded motion, brake applications. Okay, contactless. You just have to bring the magnet close. That's it. You will see it will stop. Eddy currents also has many other applications like an induction cooker, where you will see that you heat up some elements of the conductor, and that is through changing magnetic fields or through basically small eddy current loops. So all these heating or braking, retarding applications are based on eddy currents. Is that clear? Cool. So these were the things which you learned in your motional EMF. Let's start with some questions coming up on your screen. Here is the first one. The wingspan of an aeroplane is this much, the plane is flying this much, induced EMF is how much? Okay, let's try to think about this. Okay, so basically the wingspan is 36 meters. That means from here till here is 36 meters. This is basically your length. The plane is going with 400 kilometers per hour. That is your velocity. You can multiply it by 5 by 18 to convert it into meters per second. There is magnetic field also, that is also given, which is 4 into 10 to the power minus 5 Tesla. So how much is the EMF induced? Direct question, guys. It will be LVB. Everything is perpendicular. You cannot see 0 in the options. So don't be scared, sir, whether it will be 0 or what. Just multiply the length. So 36, multiply the velocity. So 400 into 5 by 18 to convert it into meters per second into magnetic field, which is 4 into 10 to the power minus 5. I think you should get the answer very easily as 0.16 volts. Okay, so solve this. So you will get this as 0.16 volts. Is that okay? Straightforward? Yes, it is option C, Pravina. Very good, very good, very good. Let's move on to the next question coming up on your screen. Diagram was interesting, right? This was asked in PMT 2014. All our, medical entrance PYQs. There is a straight conductor moved with some speed perpendicular to the field. How much EMF is induced across the conductor? These kind of direct questions have come previously, my dear students. Let's see if you guys can solve this. E is equal to LVB. The moment you see it is moving perpendicular, okay, straight wire, you can directly apply LVB. You don't have to worry about cross and dot products. Length, you can see, is 0.4. Velocity, you can see, is 7. Magnetic field is basically 0.9. 9 4s are 36. 36 into 7. So 42 and yep. So just check it out. Will it be 252 into 10 to the power minus 2, because those two decimals are there. So 2.52 volts. Is it 2.52 volts, which is again Captain Shreyas Capto is the answer. C for 2.52 volts. I can see many of you marking 2.52 volts. Very good, Pravina, Srinath, Bidisha, Acharya, very good. Keep it up. I want everybody posting the answers. Don't give up, my dear students. Next one coming up on your screen. There is a wire of length 4 meters, moves with a constant speed. If the conductor makes 30 degrees with the direction of the field in the and the field value is given, then the induced EMF is. Okay, let's try to understand. Straight wire moves at speed. The conductor is making the angle. Okay, the conductor is making an angle with the direction of the magnetic field. So if this is how the magnetic field is 0.1 Tesla, and the velocity, straight conductor moves at a speed when the conductor makes 30 degrees the direction of the magnetic field. Okay, how is it exactly moving? That is also very important, because I believe that part is missing. Conductor makes an angle and the induced. So I'm assuming that the velocity was towards us, I guess, because that's the only possible explanation that you will get a non-zero answer. Because if velocity is in the direction of the field, then V cross B will be 0. So I think I'll have to take it this way. So it will be basically 10 meters per second. So my V cross B will be upwards, somewhat like this. So this will be the direction of my V cross B. The value of V cross B will be 10 into 0.1, which is basically 1. Then the length is like this. The length is basically like this. How much is the length? 4 meters. 4 meters is the length. This angle I don't know, but I know this angle is basically 30 degrees. So naturally this angle will be 60 degrees. Why do I need that? Is because remember EMF is L dot product with V cross B. Dot product with V cross B. So it will be L into V cross B's value into cos of the theta. This will be your theta, guys. Angle between V cross B and the length. So that's why you will substitute length as 4. V cross B, I just figured it out as 1. Cos of basically 60. Cos 60 is half. So hence it will be 2 volts. Let's see whether it is 2. Yes, it is D for 2 volts. This is a very good question. People who do not know how to apply this formula will fail. So I'll just revise what we just did. Here actually it should have been given that the velocity is perpendicular to the magnetic field. That part was missing in the problem. I assumed it. So that is a missing part. It should be given in the problem. Okay. So velocity was perpendicular to the field and the length was given to be making 30 degrees. So when I did velocity cross magnetic field, I got a vector up. So that vector and the length vector. That vector and the length vector. So to replace the dot, I need cosine of the angle between these two vectors, which is cos 60. So I use cos 60 over here to find the EMF. That's how it is. Is it understood how to use this formula? Let's go ahead. Next question on your screen now. The rod is moving with some velocity perpendicular to the length. Uniform field is existing. Select the correct statement. A rod is moving. What do you think? In a direction perpendicular, constant uniform magnetic field is there. Obviously, this is a problem of motional EMF. The moving rod will behave like a battery. Battery means there is polarity, high voltage, low voltage, potential difference. That means there is electric field from high voltage to low voltage. That's it. There is electric field in the rod. As simple as that. As simple as that. So the moment you take a rod and you move it 100%, it will behave like a battery. So that means there is positive, negative polarity. That means there must be electric field in it. There must be electric field from high terminal to the lower terminal. Next question. The potential difference will be induced between the conductors if the conductor moves in. This is north pole, this is south pole of a magnet. So obviously field lines will go from your left side to the right side. This is the conductor. How will you move? Like this, or left side, or right side, or out of the plane. Try to visualize this slightly in 3D. Try to visualize this in 3D. Think about it. Come on. So Raki, for the previous question, what I just did was, if a rod moves, what does the rod moving have? It behaves like a battery. It has potential difference. It has polarities, positive, negative, high voltage, low voltage. Voltage difference means electric field. Remember, electric field always goes from high voltage to low voltage. So there is electric field inside the rod. As simple as that. It won't be from the center or anything. It is there everywhere. Everywhere it is there. So that's why option B. Is that okay, Raki? Clear? It's wrong to say the entire rod is at the same potential. Wrong. No. There will be polarities developed. That's what I just started my lecture with. Got it? Clear? Okay. So the correct answer is M for this. You can see why. Because the magnetic field will be like this. Obviously, for EMF to be introduced, V cross B should not be 0. If you notice, in this direction, velocity and magnetic field will be anti-parallel, so it will be 0. In this direction, they will be parallel, sine 0 will again be 0. Correct? And if I try to move in this direction, what happens is V cross B vector, that V cross B vector for this velocity, the V cross B vector comes out to be like this, which itself is perpendicular to the rod, rod's length. So their dot product with that length will be a 0. Dot product with the length will be 0 because this is perpendicular. Cos 90, dot means cos 90 will be 0. So the only option left is M. You can try it out. You will see that V cross B will not be 0. In fact, when length, velocity and magnetic field, all three are perpendicular, always there is an EMF. Length, velocity and magnetic field. Length, velocity and magnetic field. All three are perpendicular. Always you will see there will be an EMF. So that's why answer is B. Directly only you can go about it. Next question. Imagine an electron is coming from a faraway place and goes like this along this line. So in this loop some electricity will be created maybe. So what will be the direction of that current which is created? think about it. I think it is more about Lenz's and Faraday's law than about motional EMF alone. Gautam, we have already posted the syllabus in the Telegram channel of the test series batch. So if you are a part of the test series batch, we have shared the link long time before only. So join the Telegram group, and there only you will see the syllabus has been already posted. So please check that out. Come on, my dear students, what do you think is the answer? See, when the electron is really far away, in this loop, there will be some magnetic field because of this, because this is like a current. When an electron, which is basically a charge, which is moving, it is like a small current element. So there will be some small field. Okay. Then when it comes very close, then the field will be even higher because you are very close to the loop. Then again, when you go really far away, again the field will come back to its small value. So what do you see, my dear students? From here to here, the value of the flux increases. From here to here, the value of the flux decreases. As the electron comes close, the current comes close. So current will increase the magnetic field, so increasing the flux. As you go far away, the field decreases, flux decreases. So once the flux is increasing, once the flux is decreasing. So once the current is going this way, once the current is going that way. So the current has changed the direction. So which is that option? Option D, of course. That is the correct answer. Is that clear? No, it is not option A. A lot of people feel that no current will be introduced. That is wrong. Treat the moving electron as a current. What is current? Motion of charges. In fact, electrons only are moving. So whether it is moving in a wire or whether it is moving in free space, it's the same thing. So it is like a current carrying wire only. Okay. I'm so glad your life changed, and that is my intention, always to change your life, to touch your lives. That's the reason why I'm here, my dear students. I'm so glad. Keep it up and make sure more warriors join in this journey. It's not just you who have to join. You have to tell about this channel. You have to not only just subscribe and like, but you have to talk about us, me, the teachers, the teachings, the content, the channel, and make sure all your friends and batchmates are watching this channel. No student should be left without the knowledge coming out of from this channel. Which of the following eddy current effect is not used? Imagine this was asked in NEET 2019. Eddy current is not used. Magnetic braking, obviously it is used. Electromagnets, obviously it is used. Electric heater, no, it is I squared R which is used. The resistor loss, the Joule's heating law. Induction furnace, induction, induced EMF. So yes, it is used. So hence the answer will be electric heater. No, it is not B. Electromagnet also uses eddy currents. Okay, so when you have an electromagnet, the current which is flowing inside that electromagnet, it will create magnetic field, it will create current inside that, and there will be some loss inside that electromagnet. Again, when you turn off the current, again the field changes, again the flux changes, EMF, current, again some heat loss. So there are hysteresis losses in a electromagnet, so that is also going to make use of eddy currents. So glad Sivakumar Ayar, means a lot, bacha, means a lot. Because of you guys only, we have the strength, we have the energy, we have the motivation to conduct more classes. Without you, we are nothing. Trust me on that. Okay, so it's a symbiotic relationship, hai na? Chalo, let's see the next question. Wow, we have a rod moving and there is a capacitor connected and there is magnetic field. What more you want? All the concepts combined. Capacitance is given, length is given, magnetic field is given. Question is, what is the charge? Well, first of all, let's understand the polarity. Because the velocity is like this. Okay, velocity is like this. Magnetic field is inside. V cross B goes up. So this is the direction of V cross B. That means this will be the positive polarity, this will be the negative polarity. So this is as good as saying I have a capacitor and I have connected a battery. I have just connected a battery over here of this is positive polarity, this is negative polarity. That's all. We all know what will happen. This will have positive charge, this will have negative charge. There will be charge on it. There will be charge on it. That charge will be equal to CV. That voltage will be the induced EMF. That induced EMF will be L into V into B. That's all. Capacitance, you know, 10 microfarad. So 10 to the power minus 6. Length, you know, is 1 meter. Velocity, 2 meters per second. Magnetic field, 4. Magnetic field 4. Come on. There you go. You will get the value of the charge. And the upper charge is positive, bottom charge is negative. In fact, you don't even have to find the value. Just check. A charge will be positive, B charge will be negative. It has to be option A. No doubt about it. You can just eliminate. Anyways, the answer is going to come out to be 80 10 to the power minus 6 coulomb, which is 80 microcoulomb. So this will be the positive charge, this will be the negative charge. Option A. Right? Very good, Pravina, Priyanka, Senthil Kumar. Yep, you didn't even have to find the value. So don't get scared just because you see magnetic field, capacitor, moving rod. Sir, such a complicated question. I left the question, sir. I got scared. Nothing. Yeah, that moving rod was a battery. Have you not studied what is the charge on a capacitor when it is connected to a battery? CV. That's all. V is BLV. Nothing else was there. Let's go to the last section. And that is nothing but your inductors. Are you ready for it? Are you game for it? Are you energetic? Is the josh still high? Let me know, guys. I need some fire. I need some warming up. Okay, perfecto. Let's begin then. Let's begin. Inductors. See, any coil you take, if you change the flux through it, it will not like it. Says who? Lenz's law. You take any coil, you change the magnetic flux through it, the coil will be like, no, I don't like it. I'll oppose the change. If you try to increase, I will try to weaken you. If you try to decrease, I will try to strengthen you. Always oppose. So it always opposes the change in flux. This is actually the property of an inductor. Inductor is not a special, complicated, some crazy device. No, it's just a coil. A coil is an inductor. A normal circular coil, square loop coil, triangular coil is an inductor, which basically opposes the change in flux by Lenz's law. And the amount of electricity induced is given by by Faraday's law. Now there are two kinds of inductive properties. One is called self, one is called mutual. One is called self, one is called mutual. I'll give you two examples. Imagine there is a Pandu. Everybody knows, right, who is Pandu? Everybody remembers Pandu, long time no see. So imagine Pandu is studying, preparing for NEET. He's preparing electromagnetic induction. He's making notes, solving problems. Then suddenly he looks outside the window. Kids are playing cricket. Somebody is chit-chatting. They are playing games. Pandu is like, I should go outside also and play. I'm bored of studying. Then suddenly he remembers what Shreyas sir told. So many days are left. Shreyas sir's motivation, everything starts ringing a bell. Then Pandu is like, no, only barely 200 days, 240 days are remaining. I have to sit and study. So Pandu had the intention of going out. His motivation opposed it and he was brought back. That is called self-induction. What is it called? Self-induction. Understood? Imagine another Pandu. Case 2, scenario 2. The Pandu again is studying and Pandu is looking outside. People are playing. So Pandu is like, let's throw the books, and he starts running towards the door because he wants to play outside. From the opposite side, he gets one flying slipper with a relative velocity of 12 meters per second. He gets a flying slipper. And he also gets one tight slap. Thap karke. So his mom says, go sit and study. What are you going? Where are you going? You want one more slipper, second slipper is also ready, second hand is also ready. Pandu is like, okay boss, I will go and sit and study. That is mutual induction. You tried to do something, somebody else opposed it. Somebody else, not you, somebody else. That is mutual induction. Understood? Is that clear? Everybody with me? Okay. So, simply put, if you have a coil, and let's say there is some current through it, that current will create some polarities, north pole and south pole, of course. So there will be some magnetic field, something like this, so that there will be flux. That flux will be proportional to the current. That flux passing through the coil because of its own current, right? So flux through, if I may call this as coil number 1, this will be current 1, this will be flux 1. Flux because of its own current. That numbering is just to tell you it's because of its own. Then I can replace that proportionality with a constant. That constant is L, so that is L into I. This L is called as self-inductance. What is it called? Self-inductance, my dear warriors. The flux will be proportional to the current, because if you pass more current, more flux will be there. Less current, less flux. So that constant will be decided by the geometry, the shape and all of that. That is called as the self-inductance. So that is one formula which you should know. One of the formulas which you should know. Now just imagine there is again one coil. Again one coil is there. Here the current flowing is I1. Okay. And there is another coil besides it. There is another coil besides it that does not have any current as of now. So because of this coil's current, which produces some magnetic field, some of the magnetic field lines cut through the second coil. Some of the magnetic field lines cut through the second coil. See if you are able to visualize this. Some of the magnetic field lines from the first coil pass through the second coil, creating some flux in the second coil. Now that flux in the second coil is proportional to the current in the first coil. Understand this. The flux in the second coil is proportional to the current in the first coil, because some of the current in the first coil, some of the flux is cutting through that second one. That constant of proportionality over here is M. What is that M? This M is called as the mutual inductance. What is it called? It is called as the mutual inductance. That's all. Mutual inductance. As simple as that. Something which you should be aware of. Everyone till this point clear? Yep. Gautam, it is not there. Okay, I'll just check it out after the class is over, bacha. Okay, just give me some time. I think it was just posted. Syllabus for the upcoming test, not the entire thing. The entire thing I'll make sure it will come up by tomorrow. Worst case. Now, if I ask you what is the unit of it, well, it is simple. See, flux in general is inductance. Flux in general is basically inductance into the current. Current is in amperes. Flux is in Weber. Henry is the unit of inductance. So 1 Henry is when 1 Weber of flux passes because of 1 amperes of current. That is the unit of inductance. Obviously, inductance is a scalar quantity, and the value of the inductance depends on many things. The shape, whether it's a circle, it's a square, etc. It also depends on the size How big is it? It also depends on the magnetic materials inside. Magnetic materials inside that particular inductor. Let's find out the inductance of certain things. Say for example, we have to find the inductance of a solenoid. Imagine, this is a solenoid like this. There are many turns over here. Let's say the length of the solenoid is L. Let's say the number of turns is N. Hence, the number of turns per unit length will be capital N by L. That is also given to you. I am asking you to find the inductance of a solenoid. The question is to find the inductance of a solenoid. How to do that? Somehow show the flux is proportional to the current. The constant will become the inductance. I hope this is clear. Did I write Mi2? Oh, sorry. This is not Mi2. This is Mi1. Sorry. This is Mi1. Thank you for pointing it out. The flux in the second is dependent on the current in the first, not the current in the second. Okay, cool. Now, what I will do is, first of all, think how much will be the magnetic field inside of this B. This magnetic field we know from the previous chapter is mu naught, number of turns per unit length into the current. Whatever is the current flowing through that will decide, and the number of turns will decide how much is the magnetic field. Each field will cross each turn producing flux, but there are many such turns. So how much will be the total flux? In that solenoid? It will be flux through any one coil multiplied by n number of turns. Is that making sense? Flux through any one turn into n times. N is the total number of turns. What is the flux through any one turn? It will be the magnetic field into the area multiplied by n. But wait a minute, B is nothing but mu naught small n I into A into basically n. So now you have the option of writing small n as capital N by L. So it will become mu naught capital N by L I A N. So let me write this properly. Mu naught n square by L A into I. Do you see the flux is directly proportional to the current? Do you see that the flux is directly proportional to the current? So obviously, what will this be? This constant will be the inductance. So hence the inductance, self-inductance of a solenoid will be mu naught n square A divided by the length. This is the formula, something which you should be remembering. Is that clear? CM, you should figure out why you are procrastinating. It could be maybe because of the fear of problem solving, maybe because you feel that the concepts are difficult. Only when you see that something is boring or something is hard, that's when you feel like doing it later on. Try to start with a simpler one. Try to start with an easy chapter. Try to watch the lecture, see how I do the problems, and then do the same things by your own. Slowly, you will gain that confidence. Gain that confidence, and then you will be able to scale up. So do easy stuff, feel like doing it, and then you will never procrastinate. Hello Mani Sampath, nice to see you back. Chalo. Similarly, you can also find mutual inductance if needed. Say for example, there is one coil over here and another coil over here. This is a small radius and this is a big radius. Question is to find the mutual inductance. Find the mutual inductance. What you can do is, say this big coil is carrying some current. Because of that current, there will be some magnetic field at the center. Right? There will be some magnetic field at the center. That magnetic field is given by mu naught I by 2 times R. Remember, this was a standard formula. Due to a coil carrying current, what is the field at the center? So now if you concentrate on that small coil, there is magnetic field going like this inside of it. So obviously it has some flux. Obviously there is some flux in it. How much is the flux? The flux will be B into that area of the small coil. Area of that small coil. B value is mu naught I by 2R. Area of that small coil, won't it be pi small r square? Okay, so just rearrange the terms. Mu naught pi by 2R, this is small r square, into the current. Again I am seeing flux is proportional to the current. Flux is proportional to the current. So what will this part be? This will be the M value, the mutual inductance. This will be the mutual inductance. So that's how it is. Always show flux proportional to current. Your job is done. Okay? Is that clear? Everyone with me? Okay. Awesome. 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 Very nice. Now, once you know the flux using inductance and current, you can also find how much is the voltage created, induced EMF created if the current changes. Now, if I have an inductor, by the way, the symbol of an inductor is something like this. This is the symbol of an inductor. Let's say the current flowing through it is I. Let's say the current flowing through this is I. Imagine a situation if I is constant. If I is constant, then the flux is constant. If flux is constant, the induced EMF is 0. So basically, this inductor will just behave like a normal wire. Don't even worry that there is an inductor. If there is a constant current, don't even worry about the inductor. It will have same current, no EMF. It will just be a wire. You can replace. You just forget that there is an inductor. Replace with a wire. But the moment, imagine there is an inductor, there is a current, and this current is increasing. The moment that happens, flux will not be the same. Flux will change. Okay, the moment current is increasing, I can say the flux is increasing. So therefore the EMF is not 0. This EMF induced will oppose the change in the current. The current is trying to increase. So what will you do? You will oppose it. How will you oppose it? You can replace this with a battery like this. You can replace this with a battery like this. See if this makes sense. Why I am showing it opposite? Because I want to reduce the current, because the current is increasing. Is that clear? Is that clear? Similarly, just imagine through the inductor, okay, there is a current flowing, but this current is decreasing in nature. Again, because of the decreasing nature of the current, obviously the flux will decrease. Obviously EMF will be created. But when the flux reduces by Lenz's law, what should happen? You should help the flux. So what will you do? You will replace the inductor with one single battery like this, which will help the current. Here it is opposing, here it is assisting. So here it is opposing the increasing current. Here it is assisting the decreasing current. That's how inductors work. It does not like changes. There are some people, there are some teachers, there are some, uncle, aunts, cousins you would have met. If they decide on something, they keep doing that only. They don't like any changes. They always like to sleep at 12 o'clock, they will like to sleep at 12 o'clock. Somebody asks them to sleep early, they'll be like, no. Somebody asks them to sleep late, they'll be like, no, I will sleep at 12 o'clock. So inductor is like this. If the current is flowing, it will be like a wire. Okay, no problem. You are flowing normally. Okay, you keep flowing. Current, the moment it will be like, let me increase. Like, hey, I will oppose you. Current will be like, let me decrease. I will be like, hey, I will not allow it to decrease. So that's what inductor is. So basically, from this slide, what can you conclude? Inductor hates changes in current. or basically it resists the changes in the current. That's what you can see from this slide. Make sense, my dear students? Yeah. Priyanka, this is not exactly one shot, bacha. See, when I call it one shot, then what happens? People think one shot means teacher is going to skip everything. No, this is a marathon, detailed marathon. So if I had taken separate lectures on EMI, maybe one day I would have done one topic separately, maybe 45 minutes, 50 minutes lectures, or I don't know, maybe in 3 days or something I would have completed it. Instead, I'm doing it in one day. It will be nothing but d Li by dt, okay, and let's say the resistance is 10 ohm, let's say the current flowing is 1 ampere, okay, or maybe even let's take it as 2, oops, what just happened? Okay, it is, let's say, 2 amperes. The inductor is, let's say, 5 Henry, and the current is changing, Just check now, refresh. Is it okay? Raki will have problem solving sessions later on with PYQs, mixed problems, NCERT based questions, everything later on. First, let me complete the syllabus. Now is it fine? Just refresh. I want everybody to be back. Give me a thumbs up. Okay, now it's okay. Alright. So look at this question. Inductor is there, resistor is there, current is there, current is changing, voltage is given here. Question is find the voltage at this point. How to do these questions? Whenever you see an inductor and changing current, replace that inductor with a battery of certain voltage. See, I just told you what is the EMF in an inductor. EMF in an inductor is L di by dt. Okay. So, what will be the EMF of that inductor? It will be L di by dt. What is L? 5. What is the rate of change of current? 4. So, how much will it be? 20 volts. Okay, so this behaves like a battery, but be careful. Okay, so this is 40 volts. How will I show the battery? Will I show it like this, or will I show it like this, or like this? That's the question. So for that, see what data is given. The current is changing and it is increasing. If it is increasing, what will happen by Lenz's law? You will try to oppose it, change it by weakening it. You will try to weaken it, you will try to reduce it. So you will oppose it. So that means it will be opposite to the direction of the current. So this is 2 amperes, you will oppose it. How much is the battery voltage? 20 volts. So guys, what will be the voltage over here? If this is 40, the voltage will drop here by 20. So this will be 40 minus 20, which is again 20 volts. Everybody fine till this point? Give me a thumbs up. Everybody fine till this point? Give me a thumbs up. Clear? Understood? Pakka? Awesome. Now what is the next point? Now the next point is across the resistor. Across this resistor of 10 ohm, what will happen? There will be a drop, right? How much? 20 minus IR. I is 2, R is 10. Okay. So coincidentally, it happened that it became 0 volt. So the value of this voltage is 0 volts. That's it. 0 volts is the answer. Is that clear? Simple. So when you go across the resistor, the voltage drop in the direction of the current is IR. So this voltage minus IR is the remaining voltage. Coincidentally, it came out 0. It could have been anything else also. That's how you solve these kind of questions. Another kind of questions that you might get in inductors is the energy stored in it. So if you have an inductor, obviously there is magnetic field inside that inductor. There is field of an inductor. If you ask me, can I combine inductors like I combine resistors and capacitors? The answer is yes. So if there are two inductors in series like this, L1 and L2, the series combination formula behaves like resistors only. So treat inductors like resistors, so it will be just L1 plus L2. If there are two inductors in parallel, if there are two inductors in parallel to each other, this is L1, this is L2, then the parallel combination works like this. Just add their reciprocals, just like again resistors. So a combination is like capacitors only. There is nothing different. Okay, it's like inductors are like resistors. The capacitors are the ones which behave exactly opposite. Right? For series use parallel formula, for parallel use series formula and stuff like that. So that's how it works. Cool. So that is about inductors, inductance, energy stored in the inductor, voltages, etc. So I think we will understand this when we solve some questions. Let's try to solve some questions. You will understand. What is the self-inductance of an solenoid? Diameter has these many turns. Take 2 is equal to 10. I think this was something different. Maybe there is a misprint over here. Maybe I think mu naught value was given or something. I'm not sure. So in order to solve this particular question, what will you do? I think self-inductance of a solenoid, I just gave you the formula just some time back, right over here, if you remember. Self-inductance, mu naught n square area by length. Mu naught n square area by length. Exactly use the same thing. You will get it. Mu naught n square area by length. So mu naught is 4 pi into 10 to the power minus 7. Number of turns 500. So 500 square. Area not given, but diameter is 0.5. So radius is 0.25. So this will become pi into r square. That means 0.25 square. The whole thing divided by length. Length is 1. Solve this, you will get the answer. Solve this, you will get the answer. Just check this out. How much is the answer you are getting? Just check it. If you are getting it close to 6.25 10 to the power minus 2. Approximately 6.25 10 to the power minus 2 Henry. That is the answer. Direct application of formula, which is mu naught n square area divided by the length of the solenoid. Okay, moving on to the next question coming up on your screen. In a solenoid, if the number of turns is doubled, then the self-inductance will become, come on, I just told you the formula, you will be easily able to get it. Mu naught n square area divided by length. Length is directly proportional to the square of the turns. It is clearly mentioned in this problem. The number of turns is doubled. So n square will be 2 square times. So inductance will be 4 times. It will be quadrupled. Answer will be D. Just check this out. Yes, it is. So if you know the formulas, it becomes very simple. Or else you will keep wondering whether it will be proportional, inversely proportional, square, cube, root, whatever. So you should know the formulas. Next, coil of some inductance is given, current is also given, energy stored. These kind of questions have been asked in NEET also. Energy stored is just half Li square. Half is half, inductance is 0.5 milli, so 10 to the power minus 3 into I square, that means 2 square. One of the two cancels, so 2 into 0.5 into. Guys, it is raining outside, so I think that's why it is lagging. I think the network has some issue because it is raining outside. I'm so sorry, I cannot do anything about it, but last few problems we'll just try to complete it. Maybe in the recorded version it will come out to be nice. Okay, so that's all guys. So this will be L into 4 divided by 0.05. This will be 8. 4 goes with 8 2 times. So L will be 2 into 0.05. So it will be basically 0.1. Yes, 0.1 is there as option D. 0.1 is there as option D. Perfect. Yes, I'll be providing you the PDF also. Don't worry. Next question coming up on your screen. Solenoid has these many turns. Current is also given. Flux is also given. How much is the self-inductance? Well, if the magnetic flux linked which each turn is given, the total flux will be number of turns into flux through each turn. And this total flux is L into I. Okay, L I don't know. Current is known. Is number of turns 1000 into flux through each turn 4 into 10 to the power minus 3. 4 this L will be just 1 Henry should be the answer. This was in NEET 2016. Such a question was asked, believe me, and if you are there, I am 100% sure after this lecture you would have definitely solved this, and in the future also in any NEET exam this kind of questions come, you will be able to solve it. So you should know the definition, you should know the formula and apply it. Okay, here the keyword was each turn, so you multiply it with the turns to get the total flux, and total flux is inductance into current. I am using that concept. Let's go to the next one. Two inductors are joined in parallel. What do you think their equivalent will be? If they are in parallel, 1 by LP will be 1 by L plus 1 by L. That means it will be 2 by L is 1 by LP. Take reciprocal, it will be L by 2. So hence the answer will be just L by 2, not 2L. If they were in series, then it will be option D. It's in parallel, that's why it is L by 2. Is that clear? Just like resistors. Very good. Very good. Moving on to the next one. Two solenoids, same cross section, lengths and the number of turns are in this ratio. What is the ratio of the self inductance? Okay. I think I'll need the formula. So inductance is mu naught n square area divided by the length. So inductance is directly proportional to n square by L. So L1 by L2 will be N1 by N2 whole square, and this will be L2 by L1. That's it. No square or cube or anything. So therefore L1 by L2. What is N1 by N2? Turns ratio. Check it out. Turns ratio is 1:2. So 1:2 whole square. Then length ratio is also given. Length ratio is also 1:2. So this will be 1, this will be 2. Be careful. This is L2 by L1. L1 by L2 is 1 by 2. So L2 by L1 will be 2 by 1. So that's it. This will be 2 by 4, which is 1 by 2. So 1:2, not 2:1. So option B must be correct. Yes, very good. Some of you are very quick here. Proud of all of you who are answering like this with me. Very good. Very good. Proud of all of you. That's the answer. I think that was the last question. Now there are homework questions. Please take screenshots. This is the first question. Take a screenshot, solve it, post the answers in the comment section. Okay, after the lecture is over. Then you have this question. Okay, this is a PYQ and Kerala Common Entrance Examination for medical. So this is the second question. Take a screenshot of it. You can pause the video also. Don't worry. You can also scroll back. Then you have this particular question. Try to solve this. Paste the answer in the comment section. Okay, take a screenshot, pause, whatever. Yeah. So these are the basic questions. I want you to be little bit pushed. I want you to have that head start, so that if there is a small spark after the session, then I hope that spark converts into fire and you solve even more questions. Okay, so guys, thank you very much for attending. In fact, you should be thanking me for conducting this class. Do let me know in the comments how you loved this class, how you enjoyed this class, how you learned from this class. Obviously, there will be many more revision, problem solving, PYQs, NCERT based question solving sessions coming in the future. First priority, complete the syllabus on time. Then we can play around with the syllabus. If you try to do too much, you will not complete the syllabus, you will be tensed and you will do all random nonsense. Okay. So thank you for liking, thank you for subscribing. Take care. This is your Captain Shreyas signing off. Hasta la vista. PDF in the Telegram channel.